Alright, as promised, I have a forces problem for you guys, including stuff on inclined planes. This problem will also demonstrate static and kinetic friction. The first two I have here are for kinetic friction, and then I have a couple more problems with static friction as well. So let's start with number one here. We have a 4.8 kilogram box is sent sliding with a speed of 12 meters per second along level ground. If the coefficient of friction between the box and the ground is 0.08, how far does the box slide before stopping? So, being given an initial speed of 12 meters per second and asking how far the box slides tells us that this might end up being a kinematics problem in one way or another. Oops, that's not A, that's 1. So we know already VI is 12 meters per second, because that's the speed the box starts sliding with. We want to know how far it slides before coming to rest, so the final velocity will be 0, and we're looking for delta x. So if delta x is what we want, it's a good idea to figure out what else we need, and we could use the kinematic equation VF squared equals VI squared plus 2a delta x. If only we had the acceleration. So, this tells us to go on a little adventure to find the acceleration. And other than the kinematic equations, the main way we have to find the acceleration is to do a forces problem or an F equals ma problem. So, let's set up our F equals ma with this box. I'm going to draw myself a little picture right here. We have the box sliding to the right. I'm going to draw this VI off here separately so it doesn't get confused with our forces later. And since it's a forces problem, we want to identify the different forces we have acting. And I will just start to write them directly on the free body diagram. The box is in Earth's gravity, so it has a weight. The box is in contact with the horizontal surface, and that horizontal surface will exert a normal force up on the box. The box is moving to the right, and there is friction. So we will have friction opposing the box. Since the box is moving, it will be kinetic friction. There is no force directed to the right here. There is a velocity in that direction, but there is no force in that direction. Remember, motion itself does not tell you the forces in that direction. So with those forces now labeled on our free body diagram, we'll want to choose ourselves a coordinate system, and I'm going to pick our usual one where x is positive to the right and y is positive up. So this comprises the first couple steps of our strategy for forces problems, and now we want to move on to writing our F equals ma equations. We ultimately want the acceleration, and the acceleration will come from the x direction here. So let's start with our x equation. The sum of the forces in the x direction equals mass times acceleration in the x direction. And the next step that I want to see from you guys here is on the left side of this equation, plug in which forces we have with appropriate positive and negative signs. So we have the force of kinetic friction, opposite the direction of motion, opposite the direction of positive, so it gets a negative sign. And there is an acceleration in the x direction. That is the acceleration we are looking for. Once we get to this part, now we can plug in equations. The kinetic friction has a formula. It's the coefficient of kinetic friction times the normal force equals mass times the acceleration. Well, we were given the mass of this box, and we were given the coefficient of kinetic friction, and we want the acceleration. So what we need now is the normal force. So the x direction can't help us find the normal force, so let's try the y direction. Always right, F equals ma first. Here, our acceleration in the y direction will be 0 because this box is going to be staying on the horizontal surface. And the forces we have in the y direction are the normal force in the positive y direction and the weight in the negative y direction. Doing a little math, the normal force equals the weight, which equals the mass times gravity. This will turn out to be 47 newtons. But to demonstrate something for you guys, I'm going to leave it as mg for now. So the normal force is equal to mg, so we can take mg and plug it in for our normal force over here in our x equation. So this doesn't mean that the normal force is in the x direction. It means that the friction is in the x direction, and the formula for the friction to find out how strong it is needs the normal force in that formula. So now we're ready to start plugging in numbers, or just about. Coefficient of kinetic friction times the normal force, which we've just found out is equal to mg, equals mass times acceleration. And now right here you can see that mass would cancel out of this equation. This is telling us that the answer to the question does not depend on the mass. We would get the same answer no matter which mass of the box we had. If you ever get a problem where you aren't given the mass and you feel like you need it, work symbolically in the math like this. Call the mass m and carry it around with you until it cancels out. Or if the mass truly doesn't matter, you could just pick a value and plug it in. And since the mass doesn't matter, whether you pick 1 kilogram or 100 kilograms, you should get the same answer. Just for completeness sake, I will tell you guys what the friction force would be down here. The coefficient of kinetic friction here was 3.76 newtons. So you guys can check that yourself. But we now have a formula for our acceleration. Negative coefficient of kinetic friction times g, which is just positive 9.8 meters per second squared. So our acceleration turns out to be negative 0.783 meters per second squared. That negative is important. It tells us the box is slowing down because the acceleration is in the opposite direction as velocity. So now we can bring this acceleration that we've just found back up here to the first part of our problem and start to plug in some values. Vf squared equals 0, Vi squared, 12 meters per second, squared, plus 2 times our acceleration, and we need to keep that negative, 0.783 meters per second squared, all times delta x still. After a little bit of math, we get delta x is positive, sliding in the positive direction, 91.9 meters. So this box is going to slide quite a way before coming to rest. Now let's draw ourselves a little dividing line here and start to work on problem 2. The same box is sent sliding at the same speed up a 14-degree incline. So if we have the same coefficient of friction, now we want to know how far this box will slide up the incline. So we have the same setup for the first part here as problem 1. We have a kinetics problem or kinematic equations problem embedded within a force problem. So again, we're going to be using Vf squared equals Vi squared plus 2a delta x to find our answer. But first, we are going to need our acceleration. I'm going to leave a little space up here so I can come back and fill that in towards the end of the problem. So I'm going to draw the box on this incline here. Box is right here, the 14 degrees. If it's given as a slope or the level of incline, it's always the angle at the bottom. And we are going to want to, again, do ourselves a forces problem so that we can find the acceleration, so that we can find out the distance traveled by this box. So again, we need forces. This box is moving up the incline to begin with, so I will again label VI separate from my free body diagram, pointing up, and we will label our forces. The weight still acts straight down towards the Earth. The normal force will act perpendicular to the contact surface, so no longer straight up and down, now kind of at an angle. And the friction, again kinetic, will oppose the direction of motion. The biggest difference for this problem is that we are going to tilt our coordinate system so that our acceleration is only in the x direction and not the y direction. Everything else will remain the same, except that we're going to have to find components of our weight vector w. So we'll get to exactly how to do that in a second. But for now, let's write our F equals ma equations for the x and y directions. Sum of the forces in the x direction equals mass times acceleration in the x direction. And now we think, which forces do we have in the x direction? Well, we have the force of kinetic friction in the negative x direction, and we have a weight, or at least the x component of the weight, in the negative x direction, and that's it, equals mass times acceleration. And now we can start plugging in, or actually let's hold off on that a second. Let's write the y direction equation first here as well. Sum of the forces in the y direction equals mass times acceleration in the y direction. The forces we have in the y direction for the left side of this equation are the normal force in the positive y and the y component of the weight in the negative y direction. And there is no acceleration in the y direction because the box is staying attached to the incline as it slides up, so its y value in our tipped coordinate system is not changing. Before I go on any further now, I want to break down the vector y or w into its components. So I'm going to draw it a little bit bigger over here, trying to get things straight up and down. So one of the ways I told you guys to draw the triangle is to draw a line parallel to the y-axis from one end and a line parallel to the x-axis from another. Then that will outline your triangle for you, where this side is w, this side, with that arrow right there, is wy in the negative y direction. And this side is wx. Based on a little bit of geometry, that 14 degrees lives up here at the top of this triangle. So this means that wy is the adjacent side to that angle, which means that wy is the weight, or mg, times the cosine of theta, because it's the adjacent side. And wx is the opposite side to that angle, so wx is the magnitude of the weight times the sine of theta. Since I've given you the angle at the bottom of the incline, you can use the mnemonic I talked about in class. Sine makes it slide. So sine goes with the x component of the weight. But do be careful, because one of these days I might give you this angle phi up here, and things would be different. So this angle at the bottom is theta. That's the one we're using. All right, now we can go back to our F equals ma equations and start plugging in for any forces that have equations or components that need sines and cosines. In the x direction, we have, still negative, the coefficient of kinetic friction times the normal force, which is the kinetic friction force, minus the weight in the x direction, which we already said was the magnitude of the weight, mg, times the sine of our angle 14 degrees, equals mass times acceleration. And in the y direction, the normal force is a passive force. It has no formula. But the y component of the weight, we now know is mg times the cosine of 14 degrees equals 0. So we could do a similar process here as we did in part A to get the mass to cancel out, where the normal force is equal to mg times the cosine of 14 degrees. And we could plug this that I'm about to circle in red, this right here, in for the normal force, and our masses would cancel out again. I just want you to know that you can do that. I'm going to continue on in the problem without doing that and just working with numbers this time. So plugging in some values for the normal force, m is still 4.8 kilograms. G is still 9.8 meters per second squared times the cosine of 14 degrees. The normal force is equal to, in this case, 45.6 newtons. So note we have a smaller normal force than we did before. Now we can plug this into our x direction equation. We have negative the coefficient of kinetic friction times the normal force, that 45.6 newtons, minus the mass, 4.8 kilograms, times g, 9.8 meters per second squared, times the sine of 14 degrees, all equals the mass, 4.8 kilograms, times the acceleration, which is our unknown that we're trying to find. A little bit of rearranging can tell us that the acceleration here is, again, negative, which we should expect. This box is slowing down. But the acceleration is negative 3.13 meters per second squared. Just for completeness sake again, this time our force of, just one second. This time our force of kinetic friction is 3.65 newtons. So we actually have a slightly smaller force of friction, but we get a bigger acceleration because now it's not just the friction slowing this box down. Now we have the x component of the weight helping the friction to slow the box down. This value for our acceleration, just like before, will come back up into our kinematics problem where we can finish things up. Our final velocity is 0. Our initial velocity is 12 meters per second squared plus 2 times our acceleration of negative 3.13 meters per second squared, all times delta x. And with a little bit of math, we get delta x of, again, positive 23.0 meters. So because friction, even though it's a little smaller, now has the x component of the weight helping it out to slow this box down, the box has a greater magnitude of acceleration. It slows down quicker and does not travel as large of a distance. So these are two pretty good problems for dealing with the kinetic friction. And I'm just going to put my little copyright thing here before I move on to the other problem. What about static friction? We're going to take the same 4.8 kilogram block and place it at rest on a 4-degree incline. If the coefficient of static friction is 0.11, will the box stay at rest? So we are doing problem 3 here now. This is still a forces problem, so we're still going to want to draw ourselves a free body diagram, so let's do this. We want to know if the force of static friction is strong enough to hold the box in place. If so, we want to find its value. So the box will have, again, a force of weight. and again a normal force perpendicular. But now the box is trying to slide down the ramp if we release it from rest. So static friction is going to be opposing that by pulling the block back up the ramp, or at least trying to hold it still. These are all of our forces, and with all forces and all vectors problems, we need a coordinate system. I'm going to pick x to be positive up the ramp, and y to be positive perpendicular to the ramp, pointing in the same direction as the normal force. When trying to answer the question of will the box stay at rest, the fundamental question we're trying to answer is static friction strong enough? So to begin with, I'm going to write my F equals ma equations, and I'm going to try to figure out how strong would static friction need to be to hold this box at rest. And I guess I should probably label my 4-degree incline here. So how strong does static friction need to be? Well, static friction's in the x direction, so let's write my x equation first. Sum of the forces in the x direction equals mass times acceleration in the x direction. And based on our current free body diagram, we have the force of static friction in the positive x direction and the x component of weight in the negative x direction. And if static friction is strong enough, the box will stay at rest. And the acceleration in the x direction will be 0. From the same process we talked about earlier, we know that the x component of the weight is mg times the sine of theta, again equals 0. So the static friction needed to hold the box in place is mg sine of theta, or 4.8 kilograms times 9.8 meters per second squared times the sine of 4 degrees. Which comes out to be 3.28 newtons. So we don't have a specific formula for our static friction that will always work, but we know for this problem, if we want the box to stay at rest, the acceleration has to be 0, and if the acceleration is going to be 0, we'll need a static friction with the value of 3.28 newtons. Now we need to find something to compare this value to. So we're going to compare the needed force of static friction to the maximum force of static friction. And this is helpful because the maximum force of static friction does have a formula. It's the static friction coefficient times the normal force. Now we're going to need our y direction here. I'll go through this relatively quickly because it looks very similar to our y direction from the previous problem. Sum of the forces in the y equals may, normal minus the weight in the y direction equals 0, and it turns out that the normal force equals the y component of the weight, which was mg cosine theta, which for our new angle is, just a second. With our new angle is 46.9 newtons. So very close to the weight there. So we can now use this to plug into our equation below. The coefficient of kinetic friction is 0.11 times the normal force of 46.9 newtons gives us our maximum value of the force of static friction, which turns out to be 5.16 newtons. So now to actually answer the question, was static friction strong enough? We needed 3.8 newtons. Static friction can give 5.16 newtons. So yes, static friction is strong enough. So the question now is, what is the value of static friction? And the actual value of static friction in this problem is going to be 3.28 newtons. Static friction is a passive force, which means that it only gives as much as it needs to hold the object at rest. So here, we only need 3.8 newtons to balance out the x component of the weight, so that is all static friction gives us. It could give us more, but it doesn't have to right now. Let's draw ourselves a little dividing line here. And problem 4. At which angle will the block begin to slide? The free body diagram will be the same as the other problems here, but I'm going to redraw it anyway for a slight difference that we'll talk about. We still have the box on the inclined plane. Now we do not know our angle theta, but we still have the weight acting down, the normal force acting perpendicular to the surface, and static friction holding our box, this time at rest, or at least getting right to that point where it starts to slide. Now we need ourselves a coordinate system, and I'm going to use the same one as problem 3. So first, let's start to write our F equals ma equations. I'm going to start with the x direction again because our static friction force is in the x direction, so maybe this will help. Sum of the forces in the x equals max. In the x direction, we have the force of static friction times, or sorry, not times, what am I talking about? Minus the x component of the weight. And right at that border line between sticking and slipping, we can say our acceleration is 0. So this is a problem that is talking about an object being at the border between sticking and slipping. There's a couple specific things you can do when you have a problem like this. One of them is if we want to know one of these values, in this problem the angle, right at that border line between sticking and slipping, that means the static friction force is giving all it can give. So the static friction force is going to be the maximum static friction force, and that will turn out to be handy here soon. So I'm going to edit my free body diagram as well. Another thing to consider is the smallest angle at which the block begins to slide is the same as the biggest angle for which the block stays still. This one I should probably write down in words. So the smallest theta to slide means the same thing as the biggest theta to stick. The biggest theta to stick is more helpful for our equations because when something sticks, its acceleration is 0. And if the right side of this equation is 0, that makes our life a little easier in the math. So either smallest theta to slide or biggest theta to stick, either will answer the question at hand. I've just chosen the biggest theta for it to stay still so that we can do the math a little easier. So plugging in some formulas here. Now we can make use of the formula I wrote down earlier, that the maximum force of static friction is the coefficient of static friction times the normal force. So because we're dealing with the maximum value of static friction, we do have a formula. So mu static times the normal is the maximum force of static friction minus mg sine of theta, where now theta is our unknown, equals 0. So taking stock of what variables we have mu s, we have m, we have g. Theta is what we want, but we don't know the normal force either, so we're going to have to go find the normal force. So I'm going to come into the y direction over here. Sum of the force in the y direction equals mass times acceleration in the y direction. Since the normal force is in the y direction, hopefully this will help us out here. The normal force in the positive y direction and the y component of the weight in the negative y, and the acceleration in the y direction is 0 for the same reasons as before. So starting to do some math, the normal force equals the y component of the weight, which is mg cosine of theta. So here, we don't know the angle, so we don't really have the option of trying to calculate a value for the normal force. The only thing we have left at our disposal is to take this expression, mg cosine theta, and plug it in for the normal force in our x direction equation. So we have mu static times the normal force, which, as we just discussed, is m times g times cosine of theta, minus what else was already there, the x component of the weight, mg sine of theta, equals 0 for the reasons we discussed before. Here we can do a couple things to make our lives a little easier in the math. We can divide the whole equation by m. That cancels an m out of this term and an m out of this term. And on the right-hand side of the equation, 0 divided by m is just 0. And we can divide the whole equation by g as well. So be careful with this, because you have to cancel that term or that variable from every single term in order to cancel it out of an equation. So if we had another term like a tension force without a mass in it or without gravity, the acceleration due to gravity there, you could not cancel that out. So just be careful with your algebra. Rewriting what we have, mu static times the cosine of theta minus the sine of theta equals 0. And this is where we have to do a little bit of a math trick. And I will show you what I mean. We have a cosine of theta and a sine of theta. And if we had just one trig function, then we could take the inverse trig function to solve for the angle, because we know the static coefficient. However, we don't. So we have to rearrange things and see if we can find a way to combine these two trig functions into one. So I've added sine of theta to the other side of this equation, and to get the static coefficient by itself, I can divide both sides by the cosine of theta. The sine of theta divided by the cosine of theta is the tangent of theta. So that's a little helpful bit of trigonometry to remember for a type of problem like this. And it's about the only way that you could do this without making a computer solve it for you. Now we have the coefficient of static friction equals the tangent of theta. So theta is the inverse tangent of the coefficient of friction, or inverse tangent of 0.11. And that gives us 6.3 degrees as our maximum angle at which the block will stay stuck, or the minimum angle at which it will begin to slide. This 6.3 degree incline is the borderline between sticking and slipping in this problem. And because we're at that borderline is why we were able to use the maximum force of static friction. Look for certain words in the problem statement to let you know when you need to use the maximum force of static friction. What is the hardest the man can push? What is the fastest the car can round the corner? What is the largest angle at which the block will slide? What is the smallest angle at which the block starts to slide? These types of things, kind of extreme case language that hints that you're right at that borderline between sticking and slipping, which tells you you can use the maximum static friction. These are some good problems that bring a lot of stuff together. It's a good demonstration of our basic approach to forces problems, making sure to not forget the lines that I like to see in the math, like these two that I'm boxing right here in green. It was a good introduction to inclined planes, as well as a good few problems to draw distinction between the kinetic friction and the static friction. That's it for this video. I know it's a long one, but thank you for watching, and I will see you all in class on Monday.